Okay, so even though Chapter 4 was part of your summer assignment, I've decided to spend just a few days on it. And that's because Mrs. McCafferty's experiences, this is a section of the AP test that students have historically not done very well in. So she thought it would be worthwhile to spend a few days. So on her advice, that's what I'm doing. So really just a 3-day and then followed by probably a short test. Not a full credit test, but short test. Okay, so here we go. I think here we go. Okay, so solutions are defined, as you know, as homogeneous mixtures of two or more pure substances, right? I take some salt and I mix it in water and I have a solution. The solvent is what's present in the greatest abundance, and all other substances are considered to be the solutes, the things being dissolved. When an ionic substance dissolves in water, what happens is the solvent, and generally we're talking about water, pulls the individual ions. Okay, so here we have a water. The white parts here are the more positive side of the water. The red is the oxygen, the more negative side. So the more positive side surrounds this negative ion, let's say this is a chloride ion, and plucks it off. And on the other hand, the more negative side of the water would surround the sodium and pluck that off. Okay, and it does what we call solvates them. We call the process dissociation. So when an ionic compound comes apart in water, we call it dissociation. An electrolyte is any substance that dissociates into ions when it's dissolved. Okay? So sodium chloride is an electrolyte because it comes apart as ions in water. A non-electrolyte is something that could dissolve in water, but it doesn't dissociate into ions. It stays together as molecules. Okay? Electrolytes conduct electricity and non-electrolytes do not. This is what I wanted to show. Alright, so we have electrolytes and non-electrolytes. Now, all ionic compounds, assuming that they're dissolved, you can assume are strong electrolytes. They will completely dissociate in water. Okay? So none of them are weak and none of them are non-electrolytes. For molecular substances, all strong acids, and those are the ones you had to memorize, are strong electrolytes. Okay? All weak acids and weak bases are weak electrolytes. Remember, they only partially ionize, and it's those, because it's just partially ionized, that it makes them weak. And all other compounds are non-electrolytes. So all molecular compounds, with the exception of acids and bases, are going to be, or covalent compounds, are going to be non-electrolytes. They will not conduct electricity. So, of course, soluble ionic compounds tend to conduct electricity. And they are electrolytes. Okay. Let's keep going. Alright, so a strong electrolyte dissociates completely when dissolved in water. So this is the link I wanted to show you. Let's take a look at this.
An electrolyte is a substance that, when dissolved in water, results in a solution that can conduct electricity. The light bulb will light if the substance is an electrolyte. Sodium chloride, NaCl, is a soluble salt that is assumed to completely dissociate into ions. NaCl is a strong electrolyte when dissolved in water. The solution contains a large number of ions, and the light bulb is brightly lit. Polar water molecules interact with the positive and negative ions of the salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between the water and the salt ions causes the salt to break apart or dissolve in water. Hydrofluoric acid, HF, is a weak acid which only partially ionizes in water. HF is a weak electrolyte. The solution contains only a small number of ions, therefore the solution is weakly conducting and the light bulb is dimly lit. At equilibrium, a hydrofluoric acid solution contains mostly non-ionized acid molecules, HF, and a small amount of hydrogen ions, H+, and the conjugate base ion, F-. Methanol, CH3OH, does not dissociate into ions when dissolved in water. It is a non-electrolyte. A non-electrolyte solution does not contain ions. Therefore, the solution does not conduct electricity and the light bulb does not light. Methanol molecules contain a polar OH group. The oxygen has a partial negative charge and the hydrogen has a partial positive charge. This charge separation is called a dipole. Methanol molecules are attracted to each other through the interaction of the dipole of one molecule with the dipole of another molecule. Water is also polar, and the dipole of water will interact with the dipole of methanol. These particular dipole-dipole attractions are called hydrogen bonds. The attractions between water molecules and the methanol molecule will break the attractions between methanol molecules, causing methanol to dissolve in water. Note that upon dissolving, the covalent methanol molecules remain intact. Compare this to the dissolution of an ionic compound such as sodium chloride, NaCl, which breaks apart into its component ions in water.
Okay, I thought that was a pretty good animation. Alright, so like it was mentioned in the animation, a weak electrolyte only partially dissociates. We saw the light barely light up with hydrofluoric acid when it was dissolved in water. Okay. Alright. So strong electrolytes, again, are strong acids, strong bases, soluble ionic salts, sodium chloride, calcium chloride. Okay. Weak electrolytes are weak acids and weak bases, and non-electrolytes are everything else, mostly covalent compounds that are not acids or bases. Okay, so I asked you to memorize the solubility rules, and it's really important that you know those because you have to know how to do these. You have to know how to use these on the AP exam, and you will not have this. So do what you can to get these memorized. If you are struggling, I liked when I saw this that it was nice and pretty simple. It's going to cover 95% of what you're going to come across. You got to remember what the ions are that are always soluble. So nitrates, any of the group 1 alkali metals, anything with ammonium, anything with an acetate, anything with a chlorate or a perchlorate. So these are the things that are always going to be soluble. And then there are some that are soluble with some exceptions. So your halogens, your chlorine, bromine, and iodine, with the exception of those 3 that are pretty close to each other on the periodic table, the lead, the silver, and the mercury. And the same 3 are exceptions on the sulfates. So sulfates are going to be soluble unless they're with those 3 or the 3 that are together in group 2. Okay? So there's really no way around memorizing these. So you can go to the our Moodle page and look for the link that has flashcards you can download to memorize these. Okay, precipitation reactions. It's when we mix 2 ionic compounds that are, or aqueous solution of ionic compounds, and a solid forms. This is called a precipitate reaction. And it's actually sometimes also called a metathesis, an exchange, a double replacement. Okay, so metathesis means to transpose. And a double replacement reaction requires some driving force to proceed. Now, at least in my class for Honors Chem, the only driving force that we looked at is it had to make a precipitate, a solid. But there's actually 2 others. So we want to look to see whether or not a precipitate forms. If a precipitate forms, that means that we have a reaction that's occurred. If it doesn't form, then, and the other 2 things don't form, then that means that nothing's reacted, nothing's changed. The other thing is, and this is what you'll see mostly in acids and bases when they react, is the formation of a molecule. So water, if water is formed, that's a molecule. And if water is formed, that means that we have a reaction that moves forward. The other driving force is the formation of a gas. Okay, so let's take a look at each of the three. So if we have an insoluble compound, one that forms a solid, then a reaction occurs, right? So here's the example here is silver nitrate and potassium chloride. They're going to make potassium nitrate, which is soluble because both alkali metals and nitrates are soluble, and they're going to make silver chloride. And silver chloride is insoluble according to the solubility rules, so it's going to precipitate out, and you will have a reaction that goes forward. Okay. Hydrochloric acid is added to a solution of sodium hydroxide. So what's going to happen here is we're going to make potassium chloride and water. And that water is a molecular compound, so therefore the reaction occurs. Driving force of a gas. Now this is one that sometimes sneaks up on you. It's something you got to watch for. Okay, so it forms a gas. It either can form a gas directly, where it tells you it makes carbon dioxide or hydrogen or something you would readily recognize as a gas. And these are all the gases that eventually you should recognize as recognize the compounds that their normal state at room temperature is going to be a gas. Whoops. Carbon dioxide, sulfur trioxide, hydrogen sulfide, the stuff that smells like bad eggs, nitrogen dioxide, ammonia, oxygen, hydrogen. Okay, so eventually you'll recognize all of these as gases. But they can also come from the immediate decomposition of a product like carbonic acid, sulfurous acid, or ammonium hydroxide. So we looked at this in Chem 1, but this is going to form water and carbon dioxide. This is the gas or the product you get out of a sodium bicarbonate and vinegar, baking soda and vinegar, right? Acetic acid. You get carbonic acid, quickly decomposes into water and carbon dioxide. Whoops, this should be carbon dioxide, and this is in there as a gas, right? Just like this will break up into H2O and SO2, right? And we see that sulfur dioxide here is a gas. And this will break up into NH3 and water, right? So these things, when they form, are very temporary, and they immediately decompose into some things that include gas. So if these are your product, then you, in fact, do have a reaction. So you need to know those three. The others you'll learn over time, but you've got to be able to recognize those three, that those do become gases when they decompose. Okay. So let's take a look at this. We have hydrochloric acid is added to potassium sulfite. And when I do that, I end up with potassium chloride and in sulfurous acid. So I'm going to need 2 of these. Oops. Let me see. 2 of these. And what I know is this is going to decompose into water and sulfur dioxide. Just like if I have sodium hydroxide and ammonium chloride, this is going to make sodium chloride and ammonium hydroxide, and we just said that that's going to decompose into ammonia, which is a gas, and water. And the fact that we make this gas or make this gas tells us that the reaction goes forward, it completes. Okay, so you need to be able to write chemical equations on the AP exam, and the ones that people have most difficulty with are the net ionic. And we don't do this just with metathesis or direct replacement reactions, but double replacement reactions, we do it for all of them. And it's something you've got to get good at. And if you're good at it, then this is pretty much a guaranteed like 10 points on the on the pre-response section of the exam, because there's always going to be a question, well, at least next year there'll be a question where you have to take 3 reactions and write the net ionic. Okay? Alright, so molecular equation lists the reactants and products in their molecular form. Now, I don't like this word molecular, so this is a bit of a misnomer because it's not just molecules, it's ionic stuff too, right? So it listed in its compound form. So this would be considered a molecular equation. It shows the entire compounds in the formula. Okay? In the complete ionic equation, all the strong electrolytes and soluble salts are dissociated. So this is where you need to know what's a strong electrolyte, and those are the only things that you show breaking apart. So the silver nitrate, because it's soluble, we're going to show the silver and the nitrate separate. For potassium chloride, we're going to show the potassium and the chloride separate. But in our products, because silver chloride is a precipitate, we don't show it as ions. We show the potassium when we show the nitrate. Okay, and then to show the net ionic, what you're going to do is you're going to eliminate any ions or any substances that show up on both sides to simplify it, and you end up with this. Now, some people think it's easiest to write the complete molecular, break apart the strong electrolytes, and eliminate the spectator ions, right? Things that are on the same side. Others think it's easier to figure out what the precipitate is going to be, and then just to write what it is that produced that precipitate. So it's what you're most comfortable with. Okay, so anything that didn't change, we call those spectator ions. Those are the ions that just watch. They don't play the football game. They just sit in the stands and watch, right? They're there in the beginning. They're there at the end. Alright, so the simplest way is to write a net ionic is to write a balanced molecular equation, dissociate all strong electrolytes. So those would be your strong acids and bases and all of your ionic compounds. Cross out anything that remains unchanged as you go from the left to the right, and then the net ionic is whatever remains. Okay, so we're going to talk now about acids. Arrhenius, as you know, defined acids as a substance that produces a proton or an H+, increases the concentration of H+ when dissolved in water. Right? Bronsted and Lowry define them as proton donors, so that's really, for both of them, the same thing. There are only 7 strong acids. There are lots and lots and lots of acids, but only 7 of them are strong. So it's those that are made from those 3 same halogens we've seen before, and those that we tend to use in the lab: nitric, sulfuric, and then remember chloric and perchloric. Okay, you got to remember those. Arrhenius defined bases as substances that increase the hydroxide concentration when dissolved in water, and Bronsted and Lowry define them as proton acceptors. Bronsted and Lowry's definition is broader. It doesn't have to have a hydroxide to be a base. And if we want to know which bases are strong, it's basically the bases of these group 1 metals and the bases of these 3 that are always together here in all of our rules: calcium, strontium, and barium. So if it's a hydroxide of alkali metals or those 3 alkaline earth metals, it's going to be a strong base. Otherwise, the base will be weak. So what happens in an acid and base reaction is the acid donates a proton or an H+ to the base, right? And in the process, it becomes more like a base, and the species that accepted the H+ becomes more like an acid. Okay, so and we do know that water can act as an as an acid, and as it is in this case. It can also act as a base. We call that term, that property, amphoteric, which means it can act as either. Okay, so generally when solutions of an acid and a base are combined, the products are going to be salt and water. Okay, so here we have acetic acid. Now, acetic acid gets used a lot in the AP exam, and sometimes you see acetic acid as that with the acetate ion with the H in front, but it's also commonly written this way, so you got to be able to recognize it both ways. And even here when we do sodium acetate, the sodium actually in the book is written with the sodium in the back, and I think it actually shows that way in your notes, but I don't like it that way. The sodium really should be in the front because it's the cation, and we always show the cations first. I also, even when we do acetic acid like this, I prefer to show it this way. Now, on the AP exam, you'll get credit for either of those, but you need to be able to recognize acetic acid either in this form or in this form. Okay. So what happens is it's basically just a double replacement reaction. The H comes off the acid and partners up with the hydroxide from the base. It's just a double replacement. The sodium here, the positive cation, becomes the partner of the anion, acetate. And the fact that we get water here, molecular substance, indicates that we are making a reaction. The reaction's moving forward. Okay, so when we have a strong acid and a strong base, and we dissociate the strong acid and we dissociate the strong base, what we always end up with as a net ionic equation is hydrogen plus the hydrogen ion plus the hydroxide gives us water. Okay, always. Now, you don't have to memorize that. You ought to be able to do the dissociation and show that that's what you get. Okay? But that's what you get. So if you do memorize it, then it's a good way to check to see whether or not you have a strong acid and strong base reacting. Hopefully all of you have done some titrations, and titrations are just an analytical method where you are trying to find the concentration of a solution. Okay? And so you have an unknown concentration of a solution, and it could be an acid or it could be a base, and you're going to titrate it. You're going to put the known substance here, and you're going to figure out how much it takes to cause some change that you recognize as meaning it goes neutral. Right? So what you're looking for is the equivalence point, which is the point at which you have equal hydrogen, or sometimes we say hydronium ion, and hydroxide concentrations. The point where they're equal. And there's two ways of determining whether or not you've reached that point. One is the color change. If you use phenolphthalein, when it becomes basic, it turns pink. It goes from clear to pink. Or you see this dramatic change in pH. Okay, so you could use a pH meter and look for when you get this spike. Now the equivalence point is right here, when I have an equal amount of H plus and OH. You don't actually physically see that if you're doing it with the visual method with an indicator. What you'll going to end up seeing is, you know, the point that's a drop past the equivalence point, which is called the end point, when you know you're at the end. Okay, but you can't actually see this point because it hasn't gone basic yet. So, all right. And the way to solve concentration problems is the moles of acid are going to equal your moles of base, and because moles is molarity times volume, we can use that. Now we need to make an adjustment for how many H pluses or how many OH minuses we have on our acids and our bases. Okay, so you can use this, or you can use plain old stoic. to figure out the answer to your titration problem. So let's just take an example here. I have 42.5 milliliters of a 1.3 molar potassium hydroxide required to neutralize 50 milliliters of H2SO4. So H2SO4 is the stuff I have in my flask. I don't know what its concentration is. I'm trying to figure that out. I apologize. Look at that. I'm a terrible drawer. My H2SO4, I get some of that. Alright, wrong stuff. H2SO4 is what goes in here, okay? The H2SO4. I want to figure out what its concentration is, what its molarity is. So I take some base where I know what its concentration is. I put 1.3 molar potassium hydroxide in here, put a few drops of indicator in, and I drop by drop by drop put the potassium hydroxide in until it turns pink. When it turns pink, I determine what my volume is here, how much of the potassium hydroxide I used. I know how much sulfuric acid I started with, and I just plug it into the formula. So I'm trying to find the molarity of the acid. I know my volume. I know that H2SO4 has, it's going to make 2 H pluses. So for every 1 mole of this, I'm going to get 2 moles of hydrogen, right? Whereas for the base, potassium hydroxide, I know its molarity is 1.3. I know its volume because that's how much it took in the titration. And I know that there's only 1 OH. For every 1 mole of this, I'm going to get 1 mole of OH. So I can apply that formula. Molarity times the volume of the acid is molarity times the volume of the base. Both are adjusted for the H plus or the OH. And I plug stuff in and I find out my molarity of my base. Okay, so that's how we do a titration. And for now, until the probably the third marking period, that's all we're going to do with acids and bases. But you need to be able to do these kinds of titrations because they do come up in some of the other stuff that we do. Okay, we're going to touch a little bit on oxidation reduction reactions. We're going to do more with this later. But an oxidation occurs when an ion loses electrons, and a reduction occurs when an atom or ion gains electrons. So remember, Leo, the lion, says grr. Loss of electrons is oxidation. Gain of electrons is reduction. Okay? They always occur together. If one substance is oxidized because it's losing electrons, it's given its electrons to somebody else who's going to be reduced. So you've always got to have one with the other. Okay, so in a single displacement reaction, we are doing redox, right? There's a oxidation reduction reaction occurring. Okay, ions oxidize and ions reduce. Here we have a reaction where we put a piece of copper metal, and I think we did this one in, for most of you in the honors chem. We put a solution of silver nitrate in, and what happens is the copper displaces the silver. We're left with silver metal plating out on the copper, and we get copper nitrate solution, which happens to be blue. The copper plus 2 ions are blue. If I write the net ionic, this is what I get. Okay? Don't forget that when we have displacement reactions, or sometimes called signal replacement reactions, we need to make the judgment on whether or not the reaction is going to occur based on how reactive it is. Okay, so remember we have this activity series, and we're actually going to use standard potentials, and I'll show you that table. You should have it in your reference pack that I gave you. But the opposite reaction of what we just did, which was copper plus the copper nitrate plus silver, it's not a two-way reaction. It does not occur. And that's because if I look at my activity series, the copper is right here, my silver is right here, So the copper the silver has to be more reactive than the copper for it to replace it, and it's not, so it won't. Okay. Talk a little bit about molarity. Molarity is one way to measure the concentration of a solution. Right? Molarity is moles of a solute over volume of a solution in liters. And the molarity is used a lot in AP Chem, and it's usually how we figure out how many moles we have. And in Honors Chem, we don't do a lot with solution stoichiometry, but one of the things that we need to be aware of is that if we want to figure out moles, which is generally the key when we're doing stoichiometry, we get there by multiplying molarity times liters. Okay? So from time to time this year you're going to create a solution of known molarity, and in order to do that we have to weigh out our solid ionic compound. We use these what's called a volumetric flask. It has this little thin line that tells us exactly the volume for this size flask. Okay, so one of the things we can also do is rather than going to the stockroom and getting some solid to dissolve to make a solution, we can take a more concentrated solution and then use some of that and add water to it to make a more dilute solution. In the process we use to do that is for calculating that is the molarity of the concentrated times the volume of the concentrated is the molarity of the dilute times the volume of the dilute. Okay, so as we mentioned, we can use molarity in stoichiometry calculations. So just like we have always, we've been going from grams to moles and from atoms to moles and from volume to moles, we can also go from molarity. So if we have a solution and we know its molarity, we can use molarity times liters to give us moles. So here's an example of a molarity problem. Alright, so what volume of 0.5 molar sodium sulfate will completely react with 500 milliliters of 0.2 molar barium chloride? So let's just write the balanced equation first. It's always a good first step. Plus barium chloride, it's going to give us sodium chloride. We'll have two of those, plus barium sulfate. Okay, and what we want to know is the volume of 0.5 molar. Okay, that's going to react with this amount of barium chloride. So I'm going to take that 500 milliliters of barium chloride. Whoops. And what I know is, because it's 0.2 molar, I know 1,000 milliliters, which is a liter, is 0.200 moles of barium chloride, right? And what I know is for every 1 mole of barium chloride, I have 1 mole of sodium sulfate. Okay? And because I want 0.5 molar sodium sulfate, what I know is I want 0.500 moles of sodium sulfate per 1 liter of sodium sulfate. Okay? When I do my plug in my jug, then we will get 0.2 liters. Yep. So it's 0.200 liters of sodium sulfate. Okay, so that's how we would use molarity in a stoich problem. Alright, so let's take a look at this exercise. We have a diagram on the right represents an aqueous solution of one of the following compounds: magnesium chloride, potassium chloride, or potassium sulfate. Alright, so what we're going to look for is we've got, first of all, we have a positive 1 ion, which means it can't be magnesium, it's going to have to be potassium, right? And we've got a negative 2 ion, and the negative 2 is going to be, it's got to be the sulfate, so this has to be what I have. I can also look that I should have 2 positives for every 1 negative ion. 1, 2, 3, 4, 5, 6, 7, 8 positives and 4 negatives, so that works in that way as well. You could try these on your own, okay?